because there I can do it. Yeah, I'll do that on Monday.
Make sure there's memory and it's church. So one go.
So, in the meanwhile, since you guys have to still do this, remember that the function that can do that, this function here, a very nice function for that is called the gamma function. It's a function that represents many processes similar to this one, and therefore is very useful. It's, the way the function is usually written is, or you'll find it many times, is like this. There's a coefficient beta to the power of alpha, then the function evaluates the alpha, so you put alpha in the place of the time, and that is multiplied by the time to the power of alpha minus 1, and this is multiplied to e to the minus time divided by beta. Now, this function has several nice characteristics. First of all, when time is 0, the function is 0. When time tends to infinity, the function also becomes 0. Second, it has a sharp beginning with a maximum and then tapers down nicely. So it is kind of the type of function that we're trying to find. Also, there is a very interesting situation, which is that if alpha happens to be exactly equal to 1, then this function because gamma of 1 is equal to 1, then this function becomes 1 over beta multiplied, 1 minus 1 is 0, t to the 0 is 1, multiplied by e to the minus t divided by beta. Now this is exactly the ideal exponential decay curve. The ideal exponential decay curve is et ideal 1 over tau multiplied by e to the minus time divided by tau. So this beta in this function more or less corresponds to the average residence time. And in fact is identical to it when alpha is equal to 1 in the ideal case. What we're going to find out in our experiments is that alpha is not quite going to be equal to 1, but it's also going to be very different from 1. It's going to be larger than 1, 1.1 or maybe 1.2 or something like that, but it's not going to be much bigger than 1 normally. So our reactors don't depart too much from ideality. And the other nice thing about this function is that in Excel and in MATLAB, we have this function available in both its derivative and its integral form. Right? So that's also very convenient because we can integrate this function, no problem. Right? Sorry, we can integrate et to find this function. Now, if you were to put a line through here, that line would be your f of t calculated, there your experimental point. And it turns out that the relationship between these two curves is that this is equal to the integral between 0 and time of et dt. So both this integrated form, this integral form and the derivative form are available in many softwares. Certainly MATLAB and Excel, but also things like Mathematica, MathCAD, Maple, things like that. So what we are going to learn is how to do it in Excel by plotting our function and finding the difference between our actual data, ft experimental, and our f of t calculated, and the difference between these two. So we're Suppose one, we call it y experimental, there is y calculated. So yc minus y experimental squared gives us the square error. And then we can take the sum of all those errors and minimize it. By doing that, we're going to find a curve that has the minimum possible error. Now, what do we change so that we minimize that curve? Alpha and beta. So we're going to ask Excel or MATLAB or whatever software to find the alpha and beta values that make this curve as close as possible to our conversion data. That's the way we do it. And what I'm going to show you in a moment is how to do it in Excel. All right. So I think this is enough for our fundamental concepts. Now we're going to see actually how to do it in Excel. Or something that you like. And then the y values are presented as numbers. And then when you try to fit a line, it is going to always be a straight line that somehow goes through the origin, and that is based on these scales, right? And 1, 2, 3, 4, and 5. In fact, the data were not quite 1, 2, 3, 4, and 5. They were like 1.1, 2.2, 3.9, 4.5, 5.56. We can see them up here. Right? So they were not very precisely. And the actual flow rates here in milliliters per second, right, were put correctly. And it gave a curve of y equals 20x. And that was used by that group to calculate the actual flow rate that they needed. So they calculated that for one pump they needed a flow rate of 48, pump rate speed of 48.8, and that's their target flow rate, and for the other one 41.7. Now it turns out that the real calibration curve gives you, for that value, 2.1, which is very close to this. So this group was very lucky because when you plot the real plots, and these are called scatter plots in Excel, or XY plots. In those plots, the x-axis is plotted as a value, not as an organized category. So 1.1 is 1.1, 5.56 is 5.56, not 5. If you look at this line here, that's the fit, line fit for the experimental data. And the dotted line here, barely visible, is the wrong line, the 20x. Now it turns out that that line intersects by chance around 2.1, the other line, which means by pure coincidence, luckily, the pump was in some setting that more or less provided the right flow rate. But if we had been here, then we could have had substantially different flow rates for the same pump. And the other pump is plotted there. So that's something important to keep in mind. Use the right kind of plot. All right, so let's analyze the RTD data. So here, what we have is the original raw data. Here's the time in seconds. Here's the time actually in minutes, obtained by the expedient of divided by 60. And here's the experimental absorbance data. Right? And as you see, we have established a value of A0, which is this one, the pure crystal violet. And we have observed that this line down there ends up around 0.05. That's where it kind of tapered off. So that's going to be our equilibrium. And here we calculated this function using the corrected value, the corrected method when there is a small offset in the bottom, right? By simply finding the ratio between what I have and the total. And that is the experimental data, because they have just been calculated from the experimental data. So this would be our f of t experimental. Okay? The calculated ft is computed here, and in Excel it's used, it's called gamma distribution, right? Gamma dist, and it uses this value, this is the time, alpha, beta, and it is true that it's cumulative, meaning that we are using the integral function. Now, you've noticed that the function has alpha and beta. How do I do that? Well, each one of these cells here has a name that was given by using the, in Windows you go to formulas, create from selection, the name, define names. In Mac you have to go to tools, names, and name the range, whatever, no? Or names, I don't know where they are. It used to be in tools, now I don't know where they are. Okay, so what we do is initially we estimate values. So we say, well, let's say that this is 1. Suppose that alpha we start with a value of 1.1, and beta is something like 5 minutes or something, is what we probably had. So if we look at the plot that we get, right, this is the original data, and this is the plot with the numbers that we have. If I change the values, for example, if I change this to 6 minutes, you'll see how this changes, right? Now it's down here, right? If I change alpha to 1.2, then this curve also changes, right? All right. And now what we do is, here is the standard error, which is the experimental minus the calculated square. And the sum of all those standard errors is here. So if I click here, I get all those standard errors added up. So what we use is data solver, and we define that as a target cell. We tell it to make it minimum by changing these cells, right? The cells where we have HF, alpha, and beta. Now in my case I'm changing this EPA cell because it's a cell that I take the logarithm of that to get alpha. And then I say solve, and it gives me some solution. Now it did change only the value of beta. In this case, oh no, sorry, it didn't change any beta.
It did change beta.
Oh no, it changed beta, yeah. Let me see. Oh yeah, so it changed beta and then it made it. So this is good enough, right? It's a good enough plot. And here is our RTD and the other TET plot. So all you need to do is provide some reasonable values here. Oh, sorry, alpha. This is because I did not this. I forgot to put this equal to that. Sorry. This is equal to the natural logarithm of that guy. So now it's going to do it properly. And this guy, we're going to put it at 3.7 or something like that. Okay? So now let's change that. Solver. So now it's going to change that, which we change alpha, HF, and beta. So, okay, so now we got that HF is 0.998, it's the same as 1. HF is a multiplication in case the range is not exactly going to 1. Alpha is 1.23, beta is 4.75 minutes, and the plot, the line you see looks very, very good, very nice fit. And these are automatically calculated using alpha and beta.
Can you go back, sorry, to the first, the table? Yeah. So EFT, how is that calculated?
So now here we have already calculated these values. So EFT is the same gamma distribution function, but it has the term false here, which means it's not cumulative, meaning is derivative. So that produces the same thing. And t multiplied by et, you take the time and multiply by et, and then you get that. It's just the product of those two, and then you can plot them. And because now you know that the integral of et from 0 to infinity is 1, you don't need to divide by 1. But you have to make sure that your plot goes far enough in time. So if this is the integral that you're going to use to evaluate the integral of, this is going to be the integral from 0 to infinity of the time multiplied by e of time dt. This is what tau average is supposed to be, divided by the integral between 0 and infinity of e of t dt. But this is, by its own definition, equal to 1 already. So all we need to do is this integral. But if you take this plot and you only integrate it up to here, you are missing some part here, no? So that plot, you have to extend it until it's so small that it's negligible, right? And then that's going to give you your actual tau average. And then you can compare with the hydraulic tau. It should be smaller. If it's not, it means that probably your estimate of the volume of the tank is not correct. So that's basically that. The other analysis that I wanted to show a little bit is, this is what happens when you plot your kinetic data. And you'll see that they don't go through the origin, right? Because actually the first point that you take is like at 30 seconds. So what really matters is the slope, because it's the one that gives you K1. No? And when you plot them, you get K2. But you could also plot the intercepts, and you'll see that there is some effect of the sodium hydroxide in the dilution. It's not just straightforward. And these are the plots for the CSTR, until you get the equilibrium at the end, or the steady state. And from there, you can also calculate your conversions and your tau. No? You have to check my calculation because you have your own analysis, but that's it. Gives you an idea also of the type of graphs, how graphs look like.
Can you go back to the NaOH plot, please?
Which plate?
For the batch reactors, when you were showing the NaOH.
Batch? No, where do you mean NaOH? I'm sorry.
You mean
Here.
part of the intercepts?
You mean this one? Or the
next
intercept?
one.
This is the intercept.
Yes.
So this is the dilution of, this is my way of plotting it. We can be plotted in many different ways. This is how much the crystal violet was diluted.
Okay.
It was diluted by a factor of 2 in the first experiment, because you have 150 and 150. By a factor of 3 in the second experiment, because you had 150 and 300. And by a factor of 4 in the third experiment, because you had 100 of crystal violet and 300 of sodium hydroxide. So this is just the dilution factor for the CV, but you could plot it as another function. It's just that I had expected that the constant, the absorption was going to be, if I dilute it by a factor of 4, I should get 1/4. If I dilute by a factor of 3, I should get 1/3. If I divide by a factor of 2, I should get half of the dilution of the pure crystal violet. But I didn't quite exactly get that, right? So that means there's some small influence of the sodium hydroxide there.
Okay.
Right? Because basically what we would have expected is that eventually these intersects will tell you what was, at time 0, what was the actual initial absorbance ratio of the mix. Yeah. Now here I plotted the natural error of A over A naught, but you could plot the natural error of A. Doesn't matter, you're going to get the same value because you see whatever number you put here is not going to change this one. So you can use anything here, it doesn't matter because once you take the logarithm it becomes the offset, the intercept. There's another thing I wanted to show you in the calculation of those slopes here, is that I used a function here of Excel called line estimate. This function has to be written in a block, and when you enter it, instead of doing enter, you have to type Ctrl-Shift-Enter. And it provides you with the slope and the intercept, but it also provides you with the errors, the standard error. So it says the slope is minus 0.132 plus or minus 0.001. So you know how good your estimate of the slope is. Tells you the intersect is 0.136 plus or minus 0.003. And the same with the other one. So you can see the slopes are a very small error. Because here they are all super beautiful straight lines. There is no way to tell if it's very good or not, the fit. But at least you know the uncertainty of your parameters. And it gives you other things. This is R squared. This is the standard error in Y, meaning that if you take a value of time in that plot, the error that you make in estimating the natural logarithm of A over A naught is 0.033. That's what the standard error in Y is, and they're very similar, right? And the same here, when I plotted to find K2, it tells me, well, the slope is 5.38 plus or minus 0.048. So you can report the uncertainty of the slope instead of just putting the slope there. Right? You get some kind of statistical meaning, no? Even with an R value of 1. But there is an uncertainty in the slope. It could be 5.42 or 43, or it could be 5.35 or 33. That's the range. And again, here I use, in many places, I use names for things, right? But these are better uses of Excel, no? All right.
I'm afraid we might need to take off, Dr. Mizanti, because we've got a class at 11:35.
I have to go now. All right, so this was it.